Welcome to this explainer. You know, we look at these serene floating baskets of hot air balloons and, well, we're about to totally shatter that peaceful illusion. Today, we're going to reveal the intense physics, the roaring fire, and the complex, high-stakes mental calculations required to keep these incredible aircraft in the sky. If you've ever watched a hot air balloon drift silently overhead and wondered what's really going on up there, you are absolutely in the right place.
I mean, to truly understand how these majestic aircraft operate, we've got to look way past those beautiful views. It looks like an effortless float, right? But the reality is, a hot air balloon is a highly complex flying machine. There's no steering wheel, no brakes, literally no engine to push it forward. Instead, it is navigating this invisible, constantly shifting ocean of air.
Section 1. The magic of buoyancy. Air as a fluid.
Okay, so to really grasp ballooning, you kind of have to stop thinking of air as just empty space. You need to start treating it exactly like what it is, a complex, fluid dynamic system. In the strictest sense, a balloon isn't really flying at all. It's actually floating. It achieves what physicists call positive buoyancy, just pushing upward through this fluid-like atmosphere. It's entirely reliant on one simple fact. When you heat a gas, it expands, and it becomes less dense than the colder gas surrounding it.
So we're constantly balancing two opposing forces here. The balloon's massive fabric envelope basically just traps this expanding, less dense mass of hot air. And that captured hot air is constantly fighting against the heavier, denser ambient air outside, trying to rise up. Whenever the interior air weighs less than the displaced ambient air outside, boom, the whole system goes up.
Section 2. Anatomy of a balloon. More than just wicker and fabric.
Now, to actually harness all these crazy fluid dynamics, this seemingly simple aircraft relies on a triumvirate of highly specialized equipment to stay aloft safely. We're talking about the envelope, the heater system, and the basket. And every single one of them has to perform absolutely flawlessly. Let's look at the envelope first. Usually crafted from super strong, lightweight synthetic materials like ripstop nylon or Dacron, these things can come in some wild shapes. Whether it's your traditional teardrop or, a giant flying barn, the envelope always acts as a highly specialized heat trap. Oh, and at the very top, there's a crucial deflation port or parachute valve, which lets the pilot precisely vent hot air when they need to initiate a descent. Now, check out the sheer power of the heater system right here in this schematic. Let me tell you, this is definitely not a simple campfire keeping things cozy. A standard balloon burner system pumps out approximately 20 million BTUs of energy. That is insane. The burner actually uses its own heat to vaporize the liquid propane before igniting it, blasting this massive, roaring column of fire right up into the envelope. And hanging right underneath that 20 million BTUs of intense fire is the basket. Now, you might think they use traditionally woven wicker just for that charming vintage aesthetic, right? Actually, it's highly functional engineering. The natural flexibility and lightweight nature of wicker perfectly absorb the shock of hard landings. It bends and flexes in ways that rigid materials simply cannot. Section 3. Flight Theories in Action. Mastering Invisible Forces. So because a pilot literally cannot steer left or right with a wheel, they have to ride different wind currents to get anywhere. But here's the kicker. Flying perfectly level to catch those winds is nearly impossible. Since the air inside that giant envelope is constantly cooling down and losing lift, the pilot has to supply perfectly timed blasts from the burner, which means a balloon actually flies in a continuous series of very shallow sine waves, bobbing slightly up with a burn and slightly down as it cools, rather than in a straight, perfectly flat line. Pilots also have to account for a super fascinating but very deceptive phenomenon known as false lift. When a balloon is launching or passing into a different wind speed, the wind flowing over the curved top of the envelope actually creates temporary aerodynamic lift. It behaves exactly like an airplane wing. But as soon as the balloon accelerates and matches the wind speed, that extra lift just completely vanishes. And if the pilot doesn't quickly add heat, they are going to drop right out of the sky. Section 4. Pilot Decisions and Safety. The Mental Cockpit. This continuous, invisible dance with the wind brings us to the absolute most critical instrument on board the entire aircraft. It's not the altimeter, it's not the burner, it's the pilot's brain and the constant real-time risk calculations they're running. Just look at this staggering statistic directly from the Federal Aviation Administration. It highlights exactly why aeronautical decision-making is so paramount. Flying a balloon safety is almost entirely about human judgment.
A pilot's ability to evaluate the weather, monitor their equipment, and honestly, manage their own stress is the ultimate key to survival up there. To manage all this immense risk, pilots are trained to essentially run continuous mental software, like the DECIDE model you see here. They use systems like this alongside something called the OODA loop to systematically process information. The goal is to catch a minor discrepancy before it cascades into a full-blown emergency.
Let's actually break down that OODA loop. It requires the pilot to rapidly cycle through 4 distinct phases. First, they observe their environment, checking the winds, looking at ground tracks. Second, they orient themselves to any changes or discrepancies. Third, they decide on a correction. And finally, they act, making a physical input on the burners or those venting lines. And the crazy part? As soon as they act, the loop starts all over again. While running this loop, they're constantly balancing intense situational awareness across 3 distinct risk elements. They've got to evaluate their own physical state, like, am I too fatigued? They must know the balloon's strict performance limits. And they have to constantly scan for rapidly shifting environmental hazards. We're talking sudden weather changes, tricky terrain, or those terrifying hidden power lines. And these mental calculations, they become absolute life or death math during a high-wind landing. Keep in mind it takes about 10 seconds for a balloon to physically react to a burner blast. If a pilot is coming in for a landing in just a 15-mile-per-hour wind, they are going to travel 220 feet, that's roughly 2/3 of a football field, in those 10 seconds. The FAA actually compares this to overdriving your headlights. If the pilot isn't thinking way ahead, they're simply going to run out of time and space. But get this, even when a balloon is safely tethered to the ground, the mechanical stakes remain incredibly high. Because of the massive surface area of that envelope acting basically like a giant sail, tethered operations are generally completely grounded if wind speeds exceed a mere 8 miles per hour. Anything higher than that, and the strain on the ropes, the basket, and the anchors risks a catastrophic failure. So the next time you see a beautiful, colorful balloon floating silently by on a crisp morning, ask yourself this. Is the real marvel the fluid dynamics and the 20 million BTUs of roaring fire? Or is the true marvel the intense, invisible mental loop of the pilot, mastering their own mind to keep the whole thing perfectly balanced? Thank you for joining me for this explainer. I really hope you walk away with a whole new appreciation for the hidden intensity of ballooning.